Hello, Devices 2. This is Professor Late. Today I'm going to talk about some problems from assignment number 1. I've found out that there's a couple of problems which students are having a difficult time with, so I'm going to go over those. So the first problem we're going to talk about is this one, number 4, where it gives you a circuit and asks you for the voltage at base, the voltage at the collector, the voltage drop between the collector and the emitter, and the voltage at the emitter. This circuit is a multi-stage amplifier using two BJT bipolar junction transistors. You remember we talked about BJTs, the bipolar junction transistors, during Devices 1. So this one happens to be a NPN, because remember that the arrow points towards the negative part. And I've labeled the different leads. So on this, you have the collector, the base, and the emitter. So the first thing we're going to solve for problem number 4 is the voltage at base. So to find the voltage at base, we need to use this formula. So the formula is R2 over R1 plus R2 times the VCC. So what's the formula really talking about? It's talking about R2, which we have at 2.2 kilo ohms, divided by R1, which is 10 kilo ohms, plus R2, okay? And then multiply that by our VCC at 10 volts. So that's how you find the voltage at base. Next, we're going to find our VC, the voltage at the collector. So to find the voltage at the collector, we're going to use this formula. So the voltage at the collector is equal to the VCC minus the VRC. So the VRC is the voltage at the resistor of the collector. When we're talking about the resistor at the collector, we're talking about this one right here, the 3.9 kilo ohm resistor. And what we're looking for is the voltage drop across that resistor. So to find the voltage drop across the resistor at the collector, we need to use this formula. So we're going to take our voltage base, which we've already found, and multiply it by the resistor of the collector divided by the resistor of the emitter. So here's our circuit. So the resistor at the collector we already talked about is 3.9 kilo ohms. The resistor at the emitter, we actually have two in series. And when you have two resistors in series, their values add up, remembering back to circuits. So we have a 100 ohm resistor and a 1000 ohm resistor. So when you add those together, you get an 1100 ohm resistor at the emitter. So we know our voltage base, and we just discovered our voltage at our collector our resistance at our collector and the resistor at our emitter. So we can figure out this formula to find our voltage drop across our resistor at the collector. When you have this, you already know that the VCC is 10 volts minus your VRC, and that gets you that second value we're looking for, the voltage at the collector. So I'm going to skip one and go right to the voltage at the emitter. So we're looking at what the voltage is at the emitter. So we're going to use this formula. Voltage at the emitter is equal to the voltage at base minus the voltage drop between the base and the emitter. We already know what the voltage at base is from our first formula. So the VBE, the voltage drop between the base and the emitter, this is a PN junction. If you remember back when we were talking about PN junctions with our diodes, back towards the beginning of Devices 1, we know that they have a voltage drop of about 0.7 volts. And that's the amount of pressure it takes to overcome that PN junction. So we know what our VB is, we know what our VBE is, so we could find the voltage at our emitter. So the last value we're going to look for is our VCE, which is the voltage drop between our collector and our emitter. So to find our VCE, we are going to use this formula, where VCE is equal to the voltage at the collector minus the voltage at the emitter. So we already know the voltage at the collector, and we know the voltage at the emitter. So you can just plug those in to find your VCE. Okay, if you follow these formulas, you should be able to get the answers for problem number 4. The next problem we're going to look at states that a certain bandpass filter has a center frequency of 15 kilohertz and a bandwidth of 1 kilohertz. We need to determine the Q and classify the filter as either a narrow band or a wideband filter. So there's several ways to determine the Q of a filter. But given the information that is provided in this problem, there's really only one way to find the Q. So given the information that the problem gives us, the formula we're going to use to find the Q is we're going to divide the center frequency by the bandwidth. So we're going to divide the center frequency of 15 kilohertz by the bandwidth of 1 kilohertz. And to determine whether the filter is classified as a narrow or a wide band, we look at the Q. If the Q is greater than 10, it is classified as a narrow band. If it's less than 10, it's classified as a wide band. Next, we're going to look at the problem number 2, which states, determine the critical frequency of the low-pass filter in the diagram below, and set the value of R1 for an approximate Butterworth response. So to find the critical frequency, FC, we need to use this formula. So we have to divide 1 by 2 pi RC. Now the resistor and the capacitor that we are looking at are these ones here in parallel.